Okay, let's take a look at some open methods for finding roots. By open method, I mean we don't need brackets around the roots. Sometimes we start with 1 point, sometimes we start with 2 points, but they're not required to be on either side of the root. So let's start with Newton-Raphson. It's one of the most common and in a lot of ways the simplest ways to find roots, and it's also very powerful. If we're near the answer, it converges very, very quickly, quadratically actually. So the number of decimal places in the number of significant digits you get to the root doubles with every iteration, which is pretty powerful. If you're right to within 1%, then on the next iteration you're going to be right to within 0.01%. So let's take a look and see how this works in practice. So we've got some root, so we're drawing the line f of x equals 0 to see where that root is that we're trying to find. And we start out with xi, so if we need some guess for the root. So once we have some guess for the root, then what we do, we know that near the root that a linear approximation will be pretty good. So we know the slope of that line too. It's the derivative of f of x. So we go up to f of x, and from that value we draw a derivative line down. Now, if the function were an exact line, that would intersect exactly at the root. It's not quite a straight line, so it doesn't go quite to the root, but it gets pretty close with just one guess. Okay, so that's our new point, xi plus 1. Well, that's great if we have a graph, but what if we actually need to calculate it? So in that case, we can just use a little geometry. We know that the slope of this triangle is going to be the rise over the run. And so there, we know that f prime of x is just the rise, f of xi minus 0, divided by the run, xi minus xi plus 1. So once we've got that, we've got our slope, and then we know f of xi, we know xi, we know the derivative of f at xi, so all we need to do is figure out xi plus 1. So we just do a little manipulation here, divide both sides by f prime at xi, and the difference between xi and xi plus 1, and then we just solve that, do a little addition and subtraction, solve for xi plus 1. Now we've got xi plus 1 in terms of things we know. Xi minus f of xi divided by the derivative of f of xi. Now there's some issues with this. For example, if the slope is 0 at that point, then the denominator is 0 and it blows up. In fact, if the slope is very flat, we actually can have some real problems because it might send us off in a very wrong direction. But if we're near the root, and the root isn't exactly flat, then this can converge very quickly. So that's the first step. So the next step, we just repeat the process. We go up, we compute the derivative at that point, draw the tangent line down, and that gives us a new guess for the function. As you can see in this case, graphically, we can see that it converges to the correct answer very, very quickly. So that's Newton-Raphson. Now, one key to this is that we need to have an analytical derivative. So that's great. So if we have an analytical derivative, then we're all set. But maybe the function that we're interested in is the output of some much larger program, and we can't really go in and compute that derivative exactly. So what we need is a way to approximate the derivative. So that takes us to the secant method. So the secant method, again, we have some initial point. We actually start with 2 initial points. And then what we can do is, if those points are close together, we can approximate the derivative by we can approximate the derivative with those 2 points. If we know the function values of those 2 points, we take that difference and divide by the distance between the points. That gives us the approximate slope. That's the average slope between those 2 points. So if they're close together, it's a pretty good estimate of the slope. As you can see here, it's not quite at the tangent line, but it's pretty good. And so we draw that line down, and that gives us our new xi plus 1. So we've got our approximation for the derivative. Then all we do is we take the Newton-Raphson formula, and we plug the first equation into the second equation. Do a little bit of algebra, and now we have we've got a formula for xi plus 1. It's the same xi plus 1 that's depicted graphically on that screen. It's in terms of things we know. Xi minus 1, f of xi, and f of xi minus 1. So there we go, and then we just repeat that procedure. We need the value of the function and the value of its derivative at xi plus 1. And now we take, to compute the slope, we take our last value, xi, and the next one, xi plus 1. So now xi is taking the place of xi minus 1, and xi plus 1 is taking the place of xi. So we draw that slope, Follow the same procedure, and again we see that with this curve we get very close to the answer very quickly. That's our new xi plus 2. So one downside of the secant method is that if our gap between the two ends up being rather large, we might have a bad approximation to the derivative. Here it's pretty flat, but in other cases it might be a bad approximation. So we can approximate the derivative numerically another way, and that brings us to the modified secant method. Here we have some initial xi, but instead of having a separate xi minus 1, we have some small perturbation, some small change. And we increment the xi by that amount, and then we can compute an approximate derivative by, it's the same thing, it's the value of x of I, and the value of the function of x of I, and the value of the function of x of I plus h divided by h. So again, that gives us a derivative. That gives us a new value of xi plus 1. We follow the same procedure along. We have a new xi plus 1, and now the new value we use to approximate the derivative is not xi, it's just xi plus 1 plus some small amount. So now we compute the derivative with that slope, and that will the intersection of that line with the axis will give us our new approximation, and we keep on going. The algebra is exactly the same as with the secant method. So now we've got 3 methods that have the same basic ideas, that we want to approximate, that we want to calculate the next value in our series of approximations using the derivative, using an analytical derivative and 2 different ways of approximating a numerical derivative. There's trade-offs of different methods, of each of these methods, that they might be slightly better in different situations, and we'll talk a little bit about that later in later classes.